Good morning, everybody, and welcome to the Trusted CI webinar for November 18th, 2024. I'm your host, Jeanette Dopheide. Trusted CI is the NSF Cybersecurity Center of Excellence, and these webinars are part of its mission to deliver high-quality, actionable guidance regarding cybersecurity to the NSF community. More information about Trusted CI can be found at trustedci.org. Today's topic is privacy-preserving aggregate range queries on encrypted multidimensional databases. Our presenter is Dr. Hoda Malecki. She's an assistant professor at the School of Computer and Cyber Sciences at Augusta University. Before we begin, I have a few things to note. First, this presentation is being recorded. And second, participants are welcome to ask questions using the chat box. We're going to actually take questions at the end, so we'll be tracking them during the presentation because Hoda's colleague, Ben Fuller, is here to help respond to any questions that you have as well. So with that, I will hand things over to Dr. Malecki. Welcome.
Thank you very much, Jeanette. Good morning, everyone. I'm Hoda Malecki. I'm assistant professor at Augusta University. Today, I will be presenting the topic aggregated range query on encrypted multidimensional datasets. This work is part of the ARMOR project, which focuses on addressing key challenges in securely querying sensitive scientific datasets. ARMOR is a project funded by NSF and initiated in January 2023. It's a collaborative effort involving myself, Professor Gagan Agarwal from the University of Georgia, and Professor Ben Fuller from the University of Connecticut. The project aims to address the challenges of securely querying massive scientific datasets stored in the cloud or across organizational servers. These datasets are highly sensitive, infrequently accessed, and often critical for scientific discoveries, necessitating robust protection mechanisms that enforce both security and efficiency. Existing approaches to securing such data has significant limitations. For example, trusted hardware execution environments provide better security but face scalability challenges. On the other hand, crypto primitives such as homomorphic encryption, even though they are secure, they involve high computational overhead, making them impractical for handling large-scale datasets efficiently. In ARMOR, we try to address this gap by leveraging the searchable encryption techniques to provide both robust security and efficient query performance. Our goal is to develop a secure, efficient, and scalable framework for querying sensitive scientific datasets. This includes protecting against access pattern leakages, volume pattern leakages, while supporting advanced queries that are essential for scientific data, such as multidimensional range queries, joins, and so on. To achieve these, we are designing frameworks that integrate crypto techniques such as Boolean multimap, local sensitivity hash, and M out of N join, and so on. Under the ARMOR project, we focus on addressing key challenges in encrypted query processing for scientific data. This effort includes 3 significant works, 2 of which I will highlight now, and followed by the third one, which we will discuss in detail today. The first work, as you can see in the upper image, we studied how record retrieval strategies impact both efficiency and leakage in searchable encryption schemes. We systematically analyzed the partitioning and shuffling strategies across various dimensions and query types, demonstrating that multidimensional partitioning often yields better efficiency and security. These findings provide valuable insight for designing systems that balance performance and security in dense multidimensional datasets. In the second ongoing work, we built on these efforts by exploring the relationship between shuffling structures and indexing strategies. In this work, we aim to reduce the number of pages accessed during range queries. This helps improve efficiency while also mitigating leakage risks. We try to introduce novel shuffling structure and evaluate their performance and security impacts on real-world datasets. The third work, which we will delve into today, focuses on novel approach to secure multidimensional aggregation query. It's built on these foundational efforts to address aggregation query challenges in secure large-scale scientific database data management. So before diving into the solution, let's see what a searchable encryption is. A searchable encryption is a solution that allows the client to encrypt their data and store it on the cloud. They can then send encrypted queries to the server, and the server responds with encrypted results. This enables client to retrieve records matching a query without revealing the content of the data the query itself, without revealing the content of the data or the query that they are sending to the server. In this work, we are considering multidimensional aggregation queries, and we use searchable encryption to provide privacy of the data on the untrusted server. Aggregated queries are among the most frequently used type of queries in data analysis. Standard aggregated query, or in short SSAQ, are commonly used functions that group data tuples and compute a single value for each group. In this research, we consider aggregated operations with associated properties, including the sum, average, count, mean, max, and standard deviation on multidimensional datasets that are stored on untrusted server for storage and processing. In the area of using searchable encryption for aggregation query, only two notable works have been done so far. The first one in 2018 uses SSE, or the searchable encryption, to handle encrypted range aggregation queries for the first time. Their work presents construction for sum and minimum aggregation queries on one-dimensional dataset. However, their approach has significant limitations, including access pattern and value pattern leakages, which are inherited from the searchable encryption. Additionally, their schemes were restricted to one-dimensional data and could not support all standard aggregation queries. Their methods were most efficient for dense databases, but generalizing them to multidimensional, especially for minimum queries or minimum aggregation queries, provides complication and inefficiency. The second work, which is presented by Espritu and his group in 2022, introduces a framework for privately computing range queries, including sum, minimum, median, and null. They also proposed a domain reduction technique to improve space complexity when handling sparse databases. Despite these advantages, their scheme is still limited to one-dimensional data, lacking access pattern and volume pattern, similar to any solution that uses SSE. Moreover, their construction is approximate, failing to provide exact query results. Even their minimum scheme for aggregation solution, which was more efficient than the prior work, could not handle smaller queries, those with smaller ranges than log n, where n is the block size. These limitations highlight the gap in existing work, particularly for multidimensional and exact aggregation queries. There's been a lot of progress in using searchable encryption for range queries, but when it comes to aggregation query, as we saw, some major issues start to stand out. Most of the existing approaches are designed for one-dimensional data, which just doesn't work well for multidimensional datasets. Trying to extend them to multi-dimensions often ends up being inefficient or overly complicated, which makes them hard to apply in real-world scenarios that require flexibility. Another big problem is that many of these methods rely on approximate solution. They do not give the exact answer, which can really affect accuracy, especially if you have small range query. For example, some approaches cannot handle ranges smaller than log n, as I indicated, so they aren't very practical when you need precise results. On top of that, these solutions struggle with expressiveness. They cannot support all standard type of aggregation queries, and you often need separate methods for different type of queries. That just adds unnecessary complexity and makes it harder to adapt them to different applications. Sparse data is another area where these approaches fall short. Some methods do try to handle sparsity, but they're usually limited to approximate solutions in one dimension. They don't work well for multidimensional sparse datasets, so they miss out on opportunities to optimize performance. And then there's the security issue. A lot of these schemes leak information. For example, they can reveal which memory location are being accessed, which is the access pattern leakage, or they reveal the volume pattern leakage, which means how much data is being returned. This kind of leakages can give away sensitive details about the data and its query. With all these challenges, it's clear that we need better solutions. We need approaches that can handle all types of aggregation queries, work efficiently with multidimensional data, and takes advantage of a sparse data set. Fixing these issues is really important if you want secure, flexible, and practical aggregation query systems. Before explaining our method, I will take you through the two concepts that we use in our solution. The first one is segment tree. Segment trees were introduced by Bentley in 1977 as a way to efficiently handle aggregated range queries over arrays. Think of it as a complete binary tree built on top of an array. Each node represents a segment of the array and stores the result of a function, like the sum or min or math, which are computed over that segment. The whole structure uses a divide and conquer approach, which makes it really efficient for queries and for querying and updating by breaking down the problem into smaller segments. For example, on the left side is a one-dimensional segment tree. The array's elements are stored on the loop, which is here 1, 2, 3, 4, and the internal nodes hold the aggregation result for the respective segment. This means you can perform operations like finding the range sum or the range minimum quickly with the complexity scaling logarithmic with the size of the array. Now, when you move to multidimensional data, segment trees can be extended, as you can see on the right side. Each new dimension adds another layer, forming what's called a segment tree of segment trees, or we call it cascading segment tree. For instance, in 2 dimensions, one layer handles rows while another handles the column with each row. This step lets you efficiently perform queries and update over the region in multidimensional data set. Another concept that we use is oblivious RAM or ORAM. ORAM was introduced by Goldrich and Ostrovsky back in 1987 and later refined in 1996. The idea is simple but powerful. It allows clients to interact with untrusted memory like cloud storage, remote servers, without revealing their access pattern. Imagine if you have a memory block stored on a server like a memory block. You'd be able to access any block without the server figuring out which one you have touched. This way, even if an attacker is observing the memory, they cannot infer what data you're accessing, even if they compromise the storage system. There are many ways to build ORAM, but most of them revolve around shuffling and re-encrypting data with every access. It might sound computationally heavy, but it's a key technique for ensuring that access patterns stay hidden. Even if adversary sees which physical location are being accessed, ORAM makes it almost impossible for them to figure out the logical access pattern. In our work, we use ORAM to take security one step further by hiding access pattern during the data query. Especially important in searchable encryption because access patterns leakage can severely compromise data set security. As you will see in the next slides, we store our dataset in segment tree to ensure the server doesn't know which part of the segment tree is being accessed during a query. We store the segment tree in ORAM. This adds an extra layer of security to our system and helps to protect integrity of the data. Among all ORAM constructions, half ORAM is one of the most practical and efficient one with lot and complexity and low client storage requirement. It's the approach we use in our work, and here how it works. Path ORAM organizes data in binary tree structure, as you can see here in this image. Each node in the tree can hold a fixed number of data blocks, along with some dummy blocks to mask access patterns. The tree itself is stored on the untrusted server, with the client keeps a small amount of metadata, actually a positioning map and stash. The stash is shown here, but the positioning map is not. A positioning map keeps track of where each block is stored in the tree, while the stash serves as a temporary buffer for data during operation. When the client wants to access a block, let's say block A, it first looks up the path associated with block A in the position map. Then the client retrieves all the nodes along that path from the root of the tree to the assigned leaf node for that block and stores them in the stash. Once the path is actually fetched, the client searches for the desired block in the retrieved data stored in that stash. Now, after retrieving block A from the stash, the client, of course, can read or write, change it, the client randomly. Now, when it's done with it, the client randomly selects a new tree leaf or path to reassign the block A. Then the entire path is written back to the tree, and the position map is updated to reflect the new location. This reassignment is key to ensure that access patterns stay unpredictable, even to an adversary observing the operation. In terms of efficiency, the bandwidth overhead of the path ORAM depends on the depth of the tree, which grows logarithmic with the number of data blocks. This logarithmic overhead strikes a good balance between security and performance, making path ORAM a practical solution for scenarios where hiding data access pattern is critical without compromising too much efficiency. Using ORAM applications require thoughtful design to balance performance, storage, overhead, and security. A straightforward but kind of naive approach is to store the entire data structure as a single array within an ORAM. This approach provides a strong protection as it only leaks the total number of access and nothing about which data is being accessed. However, such simplicity comes with performance and storage costs, particularly when applied to structured data represented like a segment tree. To better understand this, consider a segment tree of size n. In this approach, the storage required becomes n log n as ORAM introduces overhead for maintaining the position map. Each query to the ORAM incurs a cost of log to the power n to the power 2n in bandwidth and a log n communication round, which represents the cost of fetch and rewriting path for each access. A single segment tree query, which may involve multiple ORAM queries, could multiply these costs by hundreds, leading to performance overhead. The key takeover here is that while ORAM ensures robust security, its application can impose significant inefficiency. The major goal of using ORAM efficiently is to gain a deep understanding of the application and its data access pattern. This enables smarter organization of ORAM, such as breaking down the data structure into smaller, more efficient units, or using hybrid approaches that minimizes the number of expense ORAM queries. By aligning ORAM design with the application-specific needs, we can achieve a balance between security, performance, and storage efficiency. This careful tailoring is critical to making ORAM practical in real-world application. This slide actually highlights our main contribution. We introduced the first multidimensional aggregation scheme based on searchable symmetric encryption, supporting standard queries like sum, mean, max, average, count, standard deviation. Our construction utilizes multidimensional segment tree for efficient query processing. To ensure access pattern protection, we actually incorporate oblivious RAM to eliminate access pattern leakage, and for volume packet protection, we designed two schemes to obscure the volume of the data returned, addressing the key security concern. We also enhanced the efficient tree traverse by doubling the number of nodes returned in query result, reducing computational and communicational overhead. Finally, through implementation and evaluation, we validated the efficiency and security of our approach, demonstrating a practical solution for secure multidimensional aggregation queries. Our design for secure standard aggregation query, or in short, SSAQ, incorporates three essential components as I indicated: the segment tree data structure, searchable encryption, and ORAM. These elements work together to ensure that aggregation queries are both efficient and secure, protecting sensitive information such as query range, access patterns, and data values. To illustrate this design, we explain the range sum query, or RSQ. RSQ actually calculates the sum of elements within a specific range of an array. It is a foundational operation used in many applications requiring aggregation or analytics over large data sets. Our approach utilizes the segment tree to optimize a range query, search encryption to secure the data, and ORAM to eliminate access pattern leakage, ensuring robust confidentiality. A naive RSQ method sums elements one by one with the time complexity of AR, where R is the range size. This becomes costly for large data sets, especially in secure systems. Using a segment tree, we reduce this logarithmic time while maintaining security, a method essentially extended to other aggregation queries like min, max, count, and sort aggregation. But here, we explain it with the sum aggregation query. As I explained, segment tree organizes data hierarchically, significantly improve the efficiency of range queries like RSQ. Array elements are stored at the leaf, while internal nodes, with this example, represent the sum of the elements in specific ranges. This structure allows a range sum queries to be performed efficiently with logarithmic time complexity for both queries and updates. The segment tree is constructed bottom-up, starting from the leaf nodes that represent individual array elements. Each internal node is computed by merging the sum of its children node. For example, in this one-dimensional dataset, the value of any internal node at index I can be calculated as the sum of its children node as 2i and 2i plus 1. Usually, this approach, the tree is pre-computed, enabling efficient query by accessing only relevant nodes. Once it's built, the segment tree is securely stored using ORAM. There's the index table, the map structure that you can see on the right side, that links the indexes to the pre-computed aggregated values. And the ORAM ensures that the access patterns are indistinguishable. This actually kind of prevents leakages, access pattern leakage, and protects the data and the query. To extend our approach, that was for one dimension. And now to extend our approach to multi-dimension, we construct a multi-dimensional segment tree by cascading the one-dimensional segment tree across each dimension. For clarity, assume this example of two-dimensional array, which is 4x4 dataset example. We start by building a one-dimensional segment tree for the X value. Here, X ranges from 1 to 4. Now, after we have done that, for each X value, that means for X1, 2, 3, 4, we create one-dimensional segment tree for the corresponding Y values. Each leaf node in the X tree is then linked to its respective Y tree. We actually proceed by merging the Y segment trees and associating the resulting Y trees to the parent nodes in the X tree, continuing this process until reaching the root node. Now, you can extend this example to more than 2 2 dimensions. We implemented our scheme and evaluated the efficiency of our approach on first 1 dimension, 2 dimension, or 3 dimension data sets. Since in our approach, actually we consider sparsity and create the segment trees based on the existing values, which are sparse. Our approach, as you can see in this table, is more efficient compared to the prior works that I explained in the related work. So as you can see, the segment tree, for example, in the Amazon books, first 1 dimension is only 15,000 nodes, while its weight is a couple of millions for the other 2 solutions. And at the bottom, you can see the data distribution graph for the kids, the 2-dimensional data set, and age for the 3-dimensional data set, which shows the sparsity of the level of the sparsity of them. Actually, ORAM only hides access pattern leakage, but it can suffer from volume leakages. So we also have volume leakage, which so far we have not addressed it or not taken care of it. In order to hide volume pattern, we bound the total number of access nodes and number of access nodes per each level of the segment tree. Then by using the bounds, we set a maximum to the number of ORAM access for each query. This actually ensures a consistent access pattern for all queries. For a segment tree of size n, the storage cost will be n log n, and each query to the ORAM requires log to the power 2n, bandwidth, and log n communication route. We actually have some claims and then present 3 main theorems to put bound on the number of return nodes and ORAM accesses. The first theorem indicates the maximum number of nodes that can be accessed in 1-dimensional segment tree during a range query, providing a clear upper bound based on the tree's height. The second theory extends this concept to multidimensional segment tree, showing how the number of access nodes increases with the number of dimensions, reflecting the added complexity of higher dimension data. Finally, the corollary ties these bounds to the performance of ORAM, demonstrating how the number of access nodes influences the total ORAM access required for secure range queries. This is an experiment we did. These graphs illustrate the number of node access at each level of the tree for different data sets, the 1 dimension, 2, and 3 dimensions. For the 1 dimension data set, as you can see, we only return at most 2 nodes at the final level of the tree and up to 4 nodes at the intermediate level. This aligns with theorem 1 of the previous slide, where the number of nodes is limited by the tree height. Similarly, for the 2 and 3 dimensions, the results scale accordingly, showing the same pattern but extending across multi-dimension. Note that without these bounds, the number of node access would grow rapidly. For instance, in the unbounded case, we could see up to 700 rounds for 1-dimensional data set and 6,000 rounds for 2 dimensions. These numbers illustrate how critical bounding is to maintain practicality, as it prevents the exponential growth that would otherwise make higher dimension data sets computationally infeasible. Once we set bounds on the number of ORAM accesses, whether for the entire tree or for each level, we propose 2 methods to hide the volume pattern leakage while keeping these things efficient. The first method, which you can see the image on the upper right side, bounds the access for the entire tree. In this case, we store the entire segment tree in a single recursive ORAM and always access the pre-computed maximum number of nodes needed for any query. To work smoothly with the ORAM constraints, the number of access is rounded up to the nearest power of 2. The second method focuses on bounding access at the level of the tree. As you can see, each level is considered as 1 ORAM. So as you can see here, each level is stored in its own ORAM. And instead of traversing the whole tree, we access only a fixed number of nodes at each level based on the pre-computed bound for that level. To keep things efficient, we can designate certain levels as stop point during queries, so we avoid traversing unnecessary parts of the tree. This actually allows us to use, the second method actually allows us to use non-recursive ORM, where the position in MAC is entirely stored at the client side. The non-recursive approach actually cuts down on the number of rounds to just one per level and supports parallel access across nodes in the same level. For the largest trees, this result is maximum of 19 rounds, which strikes a better balance between efficiency and security. By using one of these two methods, we can efficiently hide volume patterns while adjusting for different performance and security needs. Whether we bound access globally or at each level, we gain flexibility in managing trade-offs between computation, storage, and keeping query details private. Here, this actual table shows you the average of access for the second method with the bound access per level and of the ORAM. With the height, for example, with the segment tree height of 13, on average, you access 9 nodes of the tree, and for these 9 nodes, you will have 154 accesses to the ORAM. So, as we indicated prior, SSE aggregation scheme face significant limitations, which is focused mostly on one-dimensional lack explosiveness for supporting different aggregation functions. Our contribution introduced the first multidimensional SSE-based scheme capable of securely handling standard aggregation functions such as min, max, sum, average, count, and standard deviation. By leveraging multidimensional segment tree, we construct queries to support these functions efficiently. Additionally, we incorporated ORAM to protect access pattern. And we also provided 2 solutions to kind of reduce the volume pattern leakage. Throughout vertical bounds, we optimized the tree traverse for aggregation queries, ensuring efficient retrieval of results. Our evaluations confirm that this approach significantly improves support for secure multidimensional aggregation functions while addressing the limitation of prior methods. Thank you very much. I'm ready to get questions.
All right, so let me grab the screen and share some updates so that people can type in questions if they have them. And we do have a question from an audience member that I'll get to in a second here. So a couple community updates. First, the next webinar is going to be on Thursday, December 12th. Now, those of you who are frequent attendees to our webinars know that they're on Mondays, but due to scheduling constraints, we're going to move it to a Thursday, December 12th at 10 a.m. Central. And the topic is HazardMon, a unified monitoring approach to enhancing the security and resiliency of hazard workflows on heterogeneous infrastructures. Our speaker is Sunderson Kannan from Rutgers. Oh, I have an old reference here to the summit, but I actually got all of our summit videos posted yesterday. So if those of you who maybe missed the summit and want to watch those videos, you can go to our YouTube channel. And with that, let me stop sharing so I can manage my screens here a little bit better. So we had a question from Douglas, and I'm going to unmute you. Is that working? Can you unmute yourself? Okay, I think maybe it's not working. Does anyone else have any questions for our presenters? Okay, so Dr. Malecki, are you available over email if people have any follow-up questions for you?
Yeah, definitely. They
Okay.
can-
And I will be posting this video probably later today if everything goes well with getting organized. And do you have any other final comments or statements that you want to make before we wrap things up?
Nothing on my side, if Ben wants to add anything. No, we're good. Thank you very much,
All right.
everyone. Mhm.
Thank you everyone for attending, and I will see you all next month. Bye-bye.